Hi, folks. Hi, everyone. Welcome to yet another episode of Rust Rover live streams. And I'm Vitaly Bragilevsky from Rust team at JetBrains. And I'm happy that I'm joined here with Carl Lerche from Tokyo. Hi, Carl.
Hi, thanks for having me.
Uh, we, we at JetBrains, we love Rust. We love talking about Rust, everything that is Rust related. And Tokyo is not just something Rust related. Tokyo is the prominent project in the Rust ecosystem. And one amazing thing about Tokyo is that this library or this framework, they are actually having a conference this year, which is amazing, I believe. It's not just Rust conference, it's Tokyo conference. So please tell us something about that.
Yeah, thanks. We're having our first conference this year in Portland, end of April. And you can go to tokyoconf.com. I think the link's going to be shared. But the reason why I wanted to have it is it's been 10 years since we announced Tokyo. That's going to be in July. I think you actually pointed that out. I thought it was August, but I got to double check the exact date because we are going to have some sort of 10-year celebration. But anyway, since then, it's been Tokyo. I think Tokyo and Rust have become kind of one of the default ways companies and just people build infrastructure level software for networking services these days. Like if you're going to build a database or proxy or something and start from scratch, I think you would be hard pressed to not pick Rust because of the how the maturity and the correctness, all the reasons that you know and love Rust for. But it's grown to that point, and there's a big community of people building these production softwares. I thought it was time that we have a place to come together. And yes, it's called Tokyo Conf, but really it's going to be like async network programming with Rust Conf. So there'll be some other topics besides that, but the talks, the program is already posted, and I'm actually pretty excited. It was really, really hard to pick the talks, and I had a great team program committee as well that helped me out because I would not have been able to do it myself, because every single talk almost I was like, I really want to see this, because the community is building some amazing things. I've learned a lot, and I'm looking forward to learning from them as well.
By the way, why Portland?
Realistically, it's because I live in Portland and it's the easiest place for, since I'm ending up doing a lot of the organization with a partner that's helping me. So we're both in Portland, and I won't lie, I have tried to recruit other people to help organize the conference leading up to it because it's a lot of work and I didn't really want to do it. But I thought finally, all right, someone's got to do it, and it's easier to do it locally. But Portland's also a great place to visit.
Yeah, by the way, we are talking about Portland, Oregon, right?
Yeah. Don't go to Portland, Maine. Yeah.
Yeah, there are more Portlands out there, I think, in the UK. By the way, folks, so if you are listening to us, if you are on this live stream, please ask questions. If you have questions, I will ask them right away. So just in the chat, post them, and then I will ask them. So please. I have my own questions, of course, and we have an agenda here. And the idea in this live stream to talk about async Rust, Tokyo, how to write code with that, maybe some interesting facts about the ecosystem, maybe something every Rust developer should know, something about that. So we're not talking about the conference itself, but Rust, async Rust, and Tokyo. That's our main topic. So feel free to ask questions, or if you want to clarify something, also drop a message in the chat. If you want to mention where are you from, that would be also amazing. So we started with this geography thing, like Portland, Oregon, one location for this live stream. So if you are from somewhere else, please mention that in the chat. All right. So let's start simple. So when people hear async Rust, what should they actually picture in their mind?
Well, there's two things there, right? There's async and Rust. So hopefully, one, you're using the Rust programming language. I think that's obvious. But then there's the question of async, right? So Async is a general programming construct pattern. I don't think it's not new, right? It's been around forever. And a lot of people, and I want to just jump out the gun. I'm sure everyone already knows roughly what async is, but a lot of people associate async in their minds with performance and the large number of concurrent connections and that kind of concept. And it's true. It's a good way. And historically, that has been one of the driving reasons for using it. Threads and context switching has gotten better, and you can get a lot of mileage with threads. For me, async is, besides just that performance thing, it's also added flexibility with how you structure your code. And I think that is a big part that is missing. I go back to writing with threads and try to do a timeout. It is actually surprisingly hard, right? So yes, you can set a timeout on your read, on your every single blocking call, some of them at least. And you can also do interrupts. I don't know if anyone has tried doing interrupts correctly. It's quite a pain. But with async code, you can throw timeouts everywhere. It's really easy. And cancellation and managing multiple, juggling multiple in-process tasks and efficiently, not just performance-wise, but also architecturally, is a big reason to use async programming. So, in fact, I think I'm going to be a bit rambly, so you can feel free to get me back on track. But this gets back to the early days of async await. So even before that, so we're going to get to history, right? So if you're familiar with Rust, right, there's async await is the keyword, and this is it. Rust didn't invent it. That's been around for a while. I honestly don't remember where the first inventor of it, but it's a great way of doing kind of adding, dealing with callbacks and just dealing with that kind of messy programming. It's a way of doing it with syntax, and makes writing async code almost look synchronous. It really is making it look synchronous, and it's much easier, right? But anyway, so Rust has those keywords, but even before the async await keywords were added to Rust, there was this future trait. And we all, before the async Rust days, we had to write with a future trait. It was super messy, but anyway, we can get that later. But I remember when that future trait and the async patterns were being designed, cancellation and the ability of doing timeouts easily, leveraging Rust's properties, was a big driver to that, the big driver to async Rust, period. So funny enough, I think we went too far the other way and made it too easy to cancel, but that's a whole other issue. Maybe we'll get later. But with cancellation, async cancellation in Rust, you can take a future or an async block that's in progress and just drop it. And that leverages Rust's drop handler, and where you can do cleanup. And that ends up being quite nice for managing and canceling works in progress. So the main point of this is async is both performance, but also a way of managing lots of in-flight threads of logic well.
So it's also about the code quality, right? So it's easier to achieve quality with this approach.
Yes, I would say for managing lots of managing code that has lots of inbound events that can happen anytime, it's a good way to do it. And it really comes down, if you look at any sort of even UI driven development, it's all async, right? Mm-hmm. It's all event driven, async. It's kind of used interchangeably, but it is driven by reacting to events.
Right. All right. So we have here Brazil, we have England, we have California, we have Spain, San Diego, nice. California, we have Ghana,
all places I
Germany.
Want to visit.
Amazing. I like this comment very much here. Let me actually show it to everyone. I code in Rust to relax after a day of coding in every other language. Yeah, thank you very much. I think we all love Rust here.
Yeah, I will say, when we're talking about relaxing, completely non sequitur, but I actually find Java relaxing when I do it, because you don't have to worry about like making the code look nice. You just write code. There's patterns. Like, what do I name things? It doesn't matter. You just follow the patterns, come up with like something injection, builder, blah. And, it doesn't look good, but it's relaxing, I find.
All right. So we've got also Peru here in the chat, Virginia, US, another Ghana. Okay, great. So, well, let's continue. A little bit closer to Tokyo itself. And as far as I know, you were around in the early days of Tokyo, like 10 years ago. So
10 years ago, yeah, I announced it. I had to go back and find my blog post.
What was the situation back then? Like, why did Trust need something like Tokyo? Okay,
so I will say that to like understand why I ended up working on Tokyo, I got into Rust more than that. I think now, like 12. I started using Rust 12 or 13 years ago. I'm not 100% sure, but sometime around there, before the 1.0 days. And I was working actually at a company building a performance monitoring tool for Ruby. And so there's a Ruby gem, and you have to, like, we had to build collect all this instrumentation, build up structures in memory and send it out to the web service. And in Ruby, I mean, Ruby has a lot of things going for it, but performance is not one of them. And we're collecting a lot of data, and we measured our agent was taking too much of the CPU cycle. So we're like, all right, we got to switch to a native gem to do all this in native code so that we can avoid the Ruby overhead. And the obvious kind of thing was C back then, but I did a bit of C and C++, but I would not say that I was good at it. And I most likely vastly overestimated my ability to write C and C++. I'm like, how hard can it be, right? Why we have so many security issues with C code, because people like me were like, how hard can it be? But I was working with Yehuda Katz, who knew Dave Herman at Mozilla, and Mozilla then, and specifically Dave's organization, they were building Rust, this new programming language. And their reason to build Rust was experimental to see, can we come up with a safer language to build a browser with? Because browsers are incredibly security-focused pieces of software. And they're all written with C++ now. So that was kind of like their experiment. So Yehuda was like, you should try using Rust for this. And I was like, no, Rust is like, who heard of this language? No one's heard of it. It's not used by anybody. It's like before 1.0, no one's ever put in production. We're supposed to build this for a real product. No. Anyway, we had an argument. He was also working on that. He ended up winning, saying this, like, it's better to use Rust, even though it's immature, than trust my C code in production. He's right. He was right. Anyway, that's how I got into it, right? Like, I started building with it. But at that point, there was just a standard library. There's no ecosystem around it. There were like blocking socket APIs, and that's what we used. But I mean, those are just kind of like very minimal and bare bones. So incidentally, I was then like, okay, later down the road, Rust seems interesting. I want to build a side project for fun. Let me use Rust. I want to build an experiment with building a database, but I'm not going to use like blocking sockets. Let me start by binding epoll. And epoll, right, like, has a different API. I mean, like, that's a nice thing about Rust is you can easily bind C libraries, and kind of that was the MIO library, MIO. My goal there was kind of, let's see, can I bind like essentially a zero cost binding to epoll? And that ended up being the foundation of writing non-blocking IO code with Rust. Now, it was very verbose and boilerplate heavy. So you have to write, like, it is extremely, and the entire story building up to Tokyo is like, okay, this sucks working with this abstraction. Like, it's fast. It is like correct-ish. Like, it's very error prone because you're writing your state machines by hand. Let's start adding abstractions on that. And then the future trait was the very first one. And for that one, like the Rust, like a bunch of the Rust language, Rust team members worked on the future trait. I think it was like Aaron Turon and Alex Crichton were driving that future abstraction. And that was a step in abstract, like a step forward. That kind of took the concept of responding to an event and handling it, like working until as much as you can, kind of took, but it was still very manually. Like that kind of encapsulated the concept of an individual component state machine, but you were still writing your state machines by hand. And then the next step after that was designing async await. Again, those were the language team was really like looking at this problem. And what's interesting about Rust is, and I experienced this too, designing Tokio and just Mio as well, is like you want to, my first path at Mio, like you generally, I came from a like higher level language background. So I was like, let me just use callbacks. Let me just write the patterns I know from other languages using Rust. And that usually doesn't pan out super well because callbacks with Rust are like callbacks that leave the stack with Rust require you to then add send and static and a bunch of constraints to make it memory safe. And that just ends up being verbose. So that's kind of how we ended up using the future trait. And I got to say as well, async await, the way it ended up being designed is quite, I think, impressive. Like if you look in the machinery and the language constructs that get us safe async await with Rust in the zero cost abstraction way, and I don't think it was obvious that we could have, like, it could have been done. And the language designers that got us to that point I have to say, it's actually quite impressive. Anyway, I'm still very much looking back at like the design problem that they were faced with, and the answer and the solution is, they did a really good job. I don't know exactly who came up with which bit, so I'm not going to call out names there, but whoever it was involved with the async await design did a great job.
Yeah, great, really. I should show this comment, like it's a greetings from Mexico. I use Tokio in many of my personal projects, and it's fantastic. Thank you so much for creating one of the best crates. Yeah, really, thank you.
Thank you. Yeah, and it was also driven by need. I think that's why I build most of my crates as well. I will say, if anyone's writing, you should look at assert struct. I need to get more people using it. It's anyway. If you use Rust and you need to test match patterns, I'm just going to use this platform. Go look at assert struct on my GitHub, and I could use contributors there. I think it's a great.
All right, so we have some questions in chat. Interesting questions, I should say. So how about this? Could you imagine something like Java's virtual threads in Rust?
And just correct me if I'm wrong. I believe Java's virtual threads, I've not looked at it. It's similar to just the general concept of coroutines and like Go. How
yeah,
it does
maybe
Go
lightweight thing. Yeah.
So, funny enough, Rust. If you look at the history of Rust, Rust started with lightweight virtual threads and coroutines. This was well before the 1.0 days. The very early, like Rust was actually announced the same time as Go. And it was like Graydon was building like was basically an OCaml flavored version of Rust. So of Go. So there was green threads, there's everything that Go had kind of, but with an OCaml like syntax. And there was a garbage collector, lightweight virtualization, and Go took off. And Rust didn't at that point. So what I would say, like, and I don't think it was like, it's just because Google backed Go, right? I mean, like it had so much momentum, and I mean, Go is a great language for the design patterns too. Like it aims for simplicity. It's got a lot of great things going for it. But like, I would say that kind of, there wasn't a space for what Rust was initially. And the interesting thing is, like, once I kind of saw I approached Rust about the time where they added the borrow checker, and they were still removing the garbage collector and the lightweight. So there was still also the garbage collector was removed. There's the borrow checker, and then there were still lightweight green threads in Rust, and there was a whole discussion about whether or not they should stay or not. And the consensus was, let's remove them, because while it's technically possible, and again, this decision could be revisited now. The decision and the trade-offs could be very different now, but back then, Rust was heading towards a zero cost, like basically an equivalent language to performance-wise and runtime cost-wise as C or C++. And there was a lot of effort to try to see, can we make green threads like a zero cost kind of thing, but like managing the stack. There was no clean way. My recollection, and this was obviously 10 years ago, so I'm going back off of my memory, but my recollection is like figuring out how to manage a stack while growing those green threads was not obvious, and it turned out it added a lot of overhead to not using green threads as well. So the decision was, let's just rip it out completely. There's no plan for async await at this point. Obviously, it's way too early, but that was the main issue. So again, maybe if you looked at it again today, maybe there's a way of mixing zero cost, like basically native stacks with a green thread stack somehow. And my guess, it would require some sort of syntax. I don't know. I've not thought about it. The short version is, it's interesting. It used to have it and doesn't anymore.
Good. All right, folks, I have my own questions, but you know what? Your questions in the chat are better, so I will continue asking them actually. And with the next question, like I would like to expand it a little bit. So we have this question on cancellation. If you have an HTTP request in flight and you cancel the future, is the connection terminated immediately? And my expansion of this question would be, like, we know that Tokio is just one crate. There are a lot of crates that use it. So my expansion of this question is this Tokio responsibility to deal with this particular situation described here, or maybe it's something else?
Yeah. So on cancellation, short answer is it depends, but assuming you are holding the connection in that task, so there's the concept of task in the future, and the future itself owns the connection, it will get terminated immediately. So what happens is the future itself is really just a struct. It can hold the handle to the Tokio socket in as a field, essentially, in its memory. And then when you drop it, the drop handler gets called, which recursively calls drop on everything that the future contains. And once it reaches the Tokio socket, the drop implementation is to close the socket. So the short answer is yes, it will immediately close it. Now, with Hyper, for example, I believe the way it's implemented is when you use Hyper, it spawns a task, and that task is a separate Tokio task that owns that connection. And then there's some message passing between the future where you issue the requests and the actual socket. And in that case, what's going to happen is you drop the future, and that only drops like that future. It does not drop anything on the other task. Now, what happens under the hood is that message passing mechanism, like a channel, the future holds a handle to it. And hopefully I'm not using too much lingo here. Hopefully you're all following it. But the future holds a value that it uses to communicate with that other task. That value gets dropped. And if it's a Tokio channel, that sends a signal over the other task, the internal Hyper one. And then the Hyper sees that signal and knows, now I need to clean up the socket. So while if you use different tasks, there's not going to necessarily be an immediate drop, but there's going to be a whole bunch of like mechanisms built based off of Rust's drop handler to do cascading cleanup. The reason why I alluded earlier that we may have gone we may have gone too heavy. So this pattern seems very clean to me, right? Like it's very Rust-ish to say you were just using, you just drop your values and they automatically clean up after themselves. The problem comes when you write async code, right, using Rust async await, and so you have a loop, right? You're doing some work and you're not expecting that at any point in time that kind of async code can just be dropped, because let's say the caller to that async function throws it in a timeout, the timeout elapse, says that drops the future. The problem comes with just async await syntax does not expose that it can be dropped and go away at any time. So a lot of time, there's ways of dealing with it, but they're kind of, you have to know about it. And a lot of developers don't realize you have to be kind of defensive to your code can stop running at any time. And that does cause bugs. And unfortunately, it is not obvious how to best handle it. If I would if the language designers knew what they knew now, there'd probably be some slight differences in how async await would be designed. But hindsight's, was it 50? It was 2020, right? So this is what we have. I think the way forward, and still trying to figure out the best way to do it, is to have lints or some sort of warnings when that sort of pattern happens, but there's not a great way of doing it now. That's the short version. Hopefully I clarified some things.
Thank you. I'm not sure if it's it's a good question, but why would you say that Tokio won over the other async crates? What made Tokio go from one of the available async crate to the async crate? Is it the case?
I think it's not strictly the case, because there are other crates, and but they're more specialized, I think, at this point. It's not like there's an embedded one, like Embassy is an async await runtime that you use in the embedded context, and it has a very it has a design goal of being able to run without an allocator, I'm pretty sure, but I don't do embedded programming, so I don't know for sure. There are also some other IO uring first runtimes, but what I would say is, as a default, Tokio has kind of become a de facto default. And the short version is, I think it's simply because it was the first. It was the first, and that meant Hyper was built with Tokio, or all this, the ecosystem started building around Tokio, and there wasn't we're talking about just competitive details. There just wasn't a good reason to not use Tokio, because when you use Tokio, you have the ecosystem. To get rid of the ecosystem, to decide to not use the ecosystem, you need to have a very good value add, a good reason to not do it. Embassy is a good reason to not do it, to not use the Tokio ecosystem, because it's a completely different context. But for the other kind of just crates, there probably just wasn't a good reason to.
You've mentioned IO ring, and we actually have a couple of questions about that.
Yes.
I won't show them. I just summarize a little bit. So, do you have a strategy around IO ring? Maybe using it with Tokio, or?
Yes. So what I would say is, there's IO ring. It's interesting. It's a really good library to use for sure with file system APIs. It's a lot more complicated to use than EPOL. EPOL is very simple. And I would also say, while IO ring does support networking, sockets and all that, there is less of a reason to use it for that. I know there are benchmarks out there that show performance wins, but in the real world, I've seen very limited real world performance benefits using IOU ring for sockets. That's not to say there aren't any. The main reason to use it, the main performance gains that I've seen is when you have a use case where you can really where you can get a performance win from batching up syscalls. And there aren't a ton of use cases for that. So those are really going to be pretty specialized, low level cases, right? And if you are at that point, the only way you're going to really gain that benefit is if you use the IOU ring specific APIs. So to get the benefit, you need to kind of give up on the async await Tokio socket patterns. I don't see a ton of there might be some, but I've not actually seen those. We've tried, we've experimented. I've not seen real performance benefits with swapping out IOU ring for sockets under the hood in Tokio. Now, we have like Tokio U-ring. What is interesting about Tokio and the async await pattern is you can mix and match IOU ring specific APIs with Tokio, which is kind of demonstrated with the Tokio U-ring crate. So you can build out, you can have a third-party kind of IOU ring library that takes full advantages, designed, like has the socket APIs designed for using with IOU ring. And you can mix that with Tokio on the same thread. And kind of like the Tokio U-ring crate demonstrates that. Now, for file system APIs, yes, it would make sense to use it, with a caveat that historically, IOU ring has had way more CVEs and security issues than the main mature Linux APIs, which kind of puts a dampener on wanting to switch to them as the main API because of that. And there's for the file system APIs that Tokio kind of provides out of the box, and those are the ones that look like the standard library file system APIs, there's probably less of a reason to use IOU ring, because if you use those APIs, file system access is not your main use case to mix and match. Again, if file system access is like if you're building a database and you have a write ahead log, or you're pulling from like a B tree or whatnot, most likely you are going to use like APIs that touch the syscalls directly, like that mirror to the syscalls directly. And if you do that, then you can just use a third-party crate that mixes with the Tokio runtime. Okay. So that said, there is an ongoing effort by a contributor to add a IOU ring for the file system APIs. So that will most likely happen this year, I hope. I shouldn't say that because then probably won't. But anyway, there's work, and that is of interest. So the short version is, if you need IOU ring and you have a clear use case where you can gain benefits from using it, you can mix it with Tokio. But it is less clear for everyone that it is the right choice as compared to ePool, because ePool is really good. It's solid, it's mature, and it's quite optimized.
If I remember correctly, maybe a year ago or even earlier, there were some considerations about IOU ring security. So it was like there were some bugs discovered specifically connected to the ways how buffers are used there, something like that. So it's still like this comparing with ePool, which is like bulletproof for 30 years.
And it's understandable. The IOU rings API is really complicated compared to ePool again. It does but maybe that doesn't mean there are use cases for using it where there are use cases to use it there, and you can do it with Tokio. If you want to see how, look at the Tokio-U ring crate.
Okay, great. Let's zoom a little bit. If we are looking at Tokio today, what design decisions do you think really made the difference? Like the most important design decisions for Tokio?
Well, you mean Tokio itself, or writing apps with Tokio?
Well, maybe both, because they're very connected, of course.
Okay. Well, what I would say is for the Tokio runtime, for the Tokio itself, I did as little inventing as possible. Like again, I try to invent as little as possible and do what is known to work already. And when it comes to design patterns for asynchronous runtimes, there already is a wealth of prior art. I cited Go. Go is actually quite good. The runtime is quite good, and I read the source code heavily. I read the Erlang. Like Erlang is another kind of historical. Like it's built on a green threaded runtime and has a lot of years and maturity and investment in it. So why like I don't need to invent there. So in that regards, the pattern of a work stealing scheduler where you have tasks and they're kind of scheduled on the current thread and other threads kind of and the runtime manages self-balancing is a well-established pattern that works for most people. And I think I guess I'm going to be a bit rambly, but one kind of design principle for Tokio that I generally try to do for most of my Rust libraries is to have something that is easy to use for most people and good enough for most people, but have escape hatches or ways to do more specific things, right? So in networking systems and big modern servers with lots of cores, there you have to be able to manage your concurrency, your parallelization. You have to be able to keep as much locality as possible. So keep your memory on the thread, try to do as little synchronization as possible. And one way to do that is to just have one thread per core with absolutely no sharing, no work stealing, nothing. Like you just have one thread per core, no synchronization, just almost like every single thread is like an entire instant, like server, if you will. So like you assume talking between threads is really expensive and everything's isolated, and that works. And that is if you're building infrastructure level software that where like you really want to suck out like the last juice of performance and you're willing to put in the engineering work to make it work well, that is probably the design path you're going to go down, or at least evaluate. Like I think I'm going to mispronounce. Was it ScyllaDB? I don't know how to pronounce it.
Yeah, maybe.
But I think it's pronounced ScyllaDB. Like there's the Red Panda. Like there's a whole kind of that whole that whole kind of pattern of take existing big infrastructure and then rewrite it to be fast tends to use that pattern because that is a good pattern to use. That said, the downside with that is you are now on the hook to make sure every single thread you're managing the balance of work between every single thread. And if it gets out of balance, you're gonna have some threads that are underutilized, some threads that are overutilized that turns to latency. So as a default, for most people where they don't need and realistically, the vast majority of apps, even though you're using Rust and care about performance, you do not need to over prioritize performance optimization. You do not need to that level of fine tuning performance. For most people, just writing your code and letting the Tokio multi-threaded work stealing runtime, the default runtime, manage balancing work between threads is good enough. There's a bit of a synchronization cost associated with it, but in most cases, it doesn't matter. In fact, I'm even finding as Tokio and Rust get more and more kind of mainstream adoption, more and more devs are using it. It's even tried to be too smart. Like, I almost wonder if I need to even be more try to work on getting the runtime to be even more defensive against engineering mistakes. Because what I am finding is most of the time when people build apps with Tokio, they're not actually worrying about like the fine performance details of their app. And because one thing with async Rust, again, and this is the same thing with all async applications, is it's cooperative scheduling. Sorry, but the main idea is that because you're synchronizing, you're shuffling a whole bunch of different async tasks on the same thread. The thread is like the operating system thread is just going to run that task that you say to run up until it yields back to the scheduler. So there's cooperative. It's cooperative because you, as the engineer, have to make sure you're yielding back to the runtime regularly enough so that it's able to schedule other tasks. And with async await and Rust, the only time that happens is when you call .await. So when you call .await, that's the only point at which the Tokio runtime can then repurpose that thread to run a different task. So, which usually is good enough. Like in most cases, it's fine. But then if you accidentally call a CPU heavy routine there's no yielding, right? And that thread is now blocked, and not like literally blocked. Like, I mean, if you call a blocking syscall, yeah, it's blocked, but also you can consume too much CPU there, doesn't yield, it kind of stalls that thread. That can result in added latency to your app. Now, the Tokio runtime tries to mitigate that by moving tasks from that thread to other threads. But at the end of the day, like there's only so much we can do at the user level kind of in a runtime. So there's a trade-off again when you use any async runtime. You are taking on some responsibility for writing well-behaved kind of apps that yield at regular intervals.
One question from the chat here about async event being stabilized in traits. So how does it affect Tokio evolution?
Yeah, I hope we get to the point where no one needs to touch pull and pin, and that is really only used when you're writing kind of primitives that interact with Tokio. That's I don't like personally. So again, I don't think I have touched pull or pin personally, like, because I'm working on like an ORM now, and I guess we should probably talk about that at some point. But in there, I don't think I've touched pull or pin like at all, or even thought about it. So hopefully less and less. Pull and pin are really complicated. I will give you that. I mean, I don't know, like it's definitely a lot. There's a lot of concepts going there. Again, I want to go back to like the design of the language. Those concepts are very elegant, and I don't think you could have, like, given the constraints and what they get you, I would be hard pressed to come up with anything better than that. But yes, they are complicated. The flip side is I hope most developers using Tokio nowadays don't have to touch it. I'd be interesting to know, like, if there are cases in which anyone had to touch pull and pin when they weren't implementing something that inject kind of at the edge of the async Rust ecosystem, like when you're kind of integrating other things or writing primitives. If you had to touch pull and pin, I'd be interested to know why, but hopefully it is very minimal.
Right. Okay, I love this question, but actually I also love it's an icon here with lambda function and null point with 0. So what is the best way to debug async Rust?
It really depends on the use case and your preferences, I would say. These days, my go-to is, I mean, I use println a lot. I use debuggers a lot. The challenge comes, I think the biggest challenge comes when you have a stuck task, right? Like, I think for the most part, if you have any other, and I'd be interested to hear in the comments if there's any other patterns that you find specific about async Rust that's hard to debug besides stuck tasks. But we've tried over the time, like, so this Tokio console was an attempt to do that. There's also like the async backtrace crates, which try to get you access to stuck tasks, like show you where tasks are stuck. And that kind of works. It's still trying to work to get that stabilized, and there's a few challenges there. But the short version is, yes, it's challenging. I usually go to like async backtrace, debuggers, and tracing logs or print line. And honestly, at this point, LLM is actually pretty good. Claude and or whatever your preferred LLM. If you have a failing test, they're pretty good at just being like, okay, trace why and explain to me why. Those are my go-to kind of tools.
But by the way, can you imagine some non-existent tooling that would simplify developing asynchronous applications?
Simplify developing or simplify debugging?
Debugging. Yeah, I mean.
So there 100% is. Like, I think the biggest pitfall that I see really does stem down to developers accidentally canceling something and not handling the cancellation appropriately. And for that, the best way would be some sort of like lints and warnings that can catch those cancellations and just bubble them above as like, hey, this looks like a Clippy if there's a Clippy lint for this, that would be really good. And I kind of like better Clippy lints that can do full stack analysis. And this is, I've looked into this, the challenge with like, if there were better kind of static analysis Rust library found, like a library that could give you the full like Rust type system static analysis, like trait resolution and all that as a like queryable interface, it would be so much easier to build these tools that catch these patterns, or at least like highlight, hey, here are some danger zones. Here's like, this is following a pattern where it looks like something might go wrong. And my kind of hypothesis is if you could get those static analysis tools, combine them with like an LLM, like, so that gives you kind of like all that, like an entry point, and then you have a failing test, combine that with an LLM. I feel like that would actually find 90% of issues with Rust, like with the common debugging Rust issues. Now there's another problem that I get a lot, which is not like something is obviously wrong, but like I'm getting high tail latencies in my production application. Like my P99 is going up and I don't know why. That is definitely a lot harder because I mean, that's kind of like, that's hard in any language, I would say. It's like, because something is slowing down your app, and it could kind of be, there might be one main obvious thing, but it might be a combination of paper cuts. It might be like some secondary thing that's causing it. Like, so you have a symptom that's like making this HTTP call is slow, but that might just be a symptom and not the real cause kind of thing. And unfortunately, that's kind of a hard problem in any language. What I generally say there is to understand how the runtime works at a kind of like how the multi-scheduler and the yielding and the cooperative scheduling works, and generally have a good mental model of that. And then pair that with Tokio runtime metrics, because we have some good runtime metrics, and plus good instrumentation in your application, right? So one common reason for seeing high tail latencies is that cause of like, your app is not being a good cooperative scheduling citizen, I guess. So you are your chunks of logic between .await calls are too big. And to debug that, there's in Tokio runtime, there's what we call, I don't remember, poll time, histogram. There's a bunch of instrumentation for poll times. And the poll time is essentially the time spent between .await calls. And you can just instrument that, look to see like the distribution, it depends how aggressive you want to be, but like if you start seeing them more than even like in the 1 millisecond range, that's definitely starting to be something suspicious that you should go instrument. And then once you know that that's kind of the cause, then you can kind of bisect through and use other tools to figure out what it is. So I do want to go back. There was one question like, how does Tokio Console fit in this case? So I will say the disclaimer, Tokio Console was one attempt to do it. The idea was have a tool that lets you see, like that's able to see all the tasks in the system, where you can like say, hey, this task owns this socket. Show me why it's not, like, what is it waiting on before running? And I think that would be a really good tool. The first implementation kind of built on top of tracing had some issues. Anyway, it'd be nice to revisit that with the newer kind of async backtrace infrastructure. Anyway, that is the role. The role of Tokio Console was hopefully a good interface to get access to those async backtraces and debug stuck tasks.
You've mentioned earlier that you're working on ORM. Is it connected to Tokio development now? Or?
Yeah, so this kind of gets into my long-term optimistic vision for Rust, where, and I know we're kind of running out of time, and I don't know. Let's try to cram this entire big topic in like 9 minutes. But so historically, Rust kind of came to be as a systems programming language, like an alternative for C or C++ to build browsers. Primarily it was built, like Rust came to be to build a browser, but more generally to build like, anything you would have historically used C for, like games or infrastructure level software. And in that regards, I think it kind of has fulfilled its promise. Like right now, I cannot, like, for any greenfield development where you're starting something new, you don't have any constraints like you have to use a C library or I don't know, any kind of those kinds of constraints. Greenfield, if it's infrastructure level, Rust is by far your best choice for that. And kind of the reason for that, it is much easier to build software with Rust and Tokio and all that can meet some of the more stringent performance requirements. So if that is like, you have to be fast and have tight tail latencies. I don't know how much I should pick on JVM here, but no, anyway, I'm not going to. I'll be kind, but I've heard.
Yeah. By the way,
I remember
for JetBrains, JVM is the important technology. So
I just remember when I was a kid, and it was in the 90s, and I was like interested in software and game programming and all that. And I was like talking to like some software developer. I remember this. It was like, what language would be the best language to learn to get into game programming? They're like Java, because like it's going to be as fast. It's this whole promise of Java. It's going to be as fast as C or C++ because it's like the VM is going to optimize better. Anyway, I still hear that, let's just say. And I'm like, I'll just keep waiting. Like just one more GC and we're going to be there. All right. Anyway. It's all good humor poking. Ribbing, I'll take it as well on the Rust and the Tokio side. So anyway, what we're saying, I lost my train of thought, but so if you're building infrastructure level and you need reliable tail latencies, I think Rust is by far the best case. Now, if you're building higher level, like you just have maybe performance is not your main concern, and you're like a basic kind of, let's say, a backend for a mobile or web app, you may not consider Rust for that use case. And I totally understand why, because there's already really well established community, like ecosystems to build those kinds of apps. And I would say throughout my kind of Rust developer or contributor or whatever, my experience with Rust, I kind of held that belief that Rust is an infrastructure language. It is really good for that, but the cost of everything else makes it so that it's not going to be the best fit for like higher level languages because productivity is more important, et cetera, et cetera. Now I'm coming to like in my old age and old. I'm like getting more mature and be like, well, everything's not black and white, right? Like, so productivity is a complicated thing, and Rust has gotten a big foothold in organizations because by virtue of it being really, it has a really clear use case. It gets established in organizations. And what I see is like that. Remember when I said like Rust is the best tool for greenfield development for this because you may have to pull in libraries and whatnot, and the ability to pull in existing libraries for your use case has a big impact on productivity. The same is actually the other way. You inject Rust in your business or your company, start using it for a clear use case. You start onboarding your developers, they learn Rust. You start building your internal tooling for Rust. You start building internal libraries for that one use case. And now you have like maybe now I'm going to build like a web app for this infrastructure level tool where performance isn't the most critical thing, but like, wow, wouldn't it be nice to build with Rust because I have all these other libraries for this thing, internal libraries and infrastructure and build and et cetera, et cetera. Like, yes, maybe in theory, building with this as a Node app would, or whatever, TypeScript, whatever. Dino, I don't know. I'm not following it too closely. I like Dino. Dino's built with Tokio. I'm a big fan. If you got to do something, use Dino. Anyway, yes. So maybe in theory, a greenfield, again, if you're building the same kind of thing, you would be better off, more productive with a JavaScript-based ecosystem. But you have all these libraries, so you actually want to build with Rust. So I think there is going to be an expansion of Rust in these higher level use cases, and I'm seeing it happen today. Users are trying to do this, but hit kind of like the ceiling where, well, the libraries at this higher level just don't exist. Like Rust has a really, really established and mature ecosystem at lower level. Like, how many other languages can you really get like an app, like a library like Tokio, and then a really good font rendering library, and then a good like GPU kind of library? Like, this is actually like the breadth of use cases you can do with Rust well is staggering. But once you get to that higher level, there's less there because no one's tried to build it. So I think, and as I'm getting to it, I think Rust actually could be a really nice language to build higher level web apps, even for greenfield. Because while initial prototyping might be Rust may not be the best prototyping language, it has a lot of nice properties for long-lived applications. Like the type system is really nice. Like the performance, like who would say no to better performance even if it's not needed, right? Like it's got a lot of nice properties. The productivity side is lacking at that higher level. I am coming, and I may just be heavily biased, but I'm wondering how much of that is inherent to the language versus the lack of ergonomic libraries, plus libraries that put less of a focus on less emphasis on maximizing raw performance versus productivity, right? So I think because of the history and the background of systems level language that Rust has, a lot of the libraries we have today are kind of focused on this zero cost abstraction at the expense of ease of use. So like overusing traits or like lifetimes and traits are really good features even at a higher level, but they can be abused and they can be hard to use. And I have been there as well. So I mean, like I've written libraries that I would say, like going back and looking at them, Conf tower. Anyway, sorry. I would not do it again that way. Like the way it's designed, like the trait insanity is high. So I understand, and I understand like the evolution that went through. There's also like a lot of like being back, like coming to Rust from a like more dynamic languages. Like this trait system's awesome. We can like prevent all errors from ever happening in runtime because by having like modeling every state change in traits, and technically true, you avoid errors in production because you never get there because it doesn't ever come. Anyway, So there's a balance I think we got to find. And I do think there's a way to build productive and ergonomic like libraries with Rust that focus on ease of use. And I'm trying to do that with Toasty. So like Toasty is on the Tokio GitHub repo because that's where I work. It's easier to just pull in contributors and team management. Anyway, it's there. It's marked as incubating. I'm hoping to announce like beta and all that at Tokyo Conf. Spoiler, but anyway, where it's pretty close, I think, to being at the point where it's usable for applications. I got some people trying it. I would love for anyone to try out Toasty, the ORM, give me feedback, what's missing, to use it for real apps. It's also because it's an ambitious goal. I'll say that. I'm happy to talk more about Toasty. That's probably a whole other topic. But the main point is I'm trying to design it to be a higher level thing. I'm going to, after Toasty, I'm going to try to look at how easy can we make building like your more traditional web app with Rust. That's kind of going to be the exploration. And maybe not, and it's not to replace TypeScript apps. Like I do think like those are probably going to be what most people use. But like I said, I think there's going to be more and more of a use case for building these higher level web apps with Rust because your organization is already invested in Rust. And it'll just make it easier. Oh, someone's asking for the URL.
Yeah.
I'll try to, someone else can pull it. Otherwise I will.
Yeah, please. Like I think it's GitHub Tokyo RS.
Tokyo
right?
-rs -toasty, I think.
Yeah, it should be there. Yeah. Actually, like one more question about this, like high level frameworks. Like when we at JetBrains, when we look at the programming language, one thing is supporting the language, but the other thing is always supporting some big frameworks in that area. For example, when we talk about Java or Kotlin, we have Spring Boot there, and we provide features for these particular libraries. When we look at Rust space, like for years, it was very difficult to figure out like which web framework we should support with additional features. Like now we have like Axum, for example. Axum from Tokyo ecosystem is getting a lot of attention these days. But we definitely see the lack of high quality industrial level, high level application framework for Rust. So do you think this will happen one day?
For web apps, you mean? Because there's also like the
web
front end.
apps.
I think so, because that is my goal. So that is what I'm working on. And my kind of background is I got like a big chunk of my kind of professional career early on was working with Ruby on Rails. And I actually was like a contributor. Like I was on the core team for a bit, and building and in the kind of, and for me, like one big defining moment in my career and just how I thought about software really was, and I don't know if I feel old now. I don't know if anyone remembers the kind of when Ruby on Rails was announced that Screencast build a build a blog in 15 minutes or less or something like that. I think it was a blog.
Yeah.
I don't know how many people remember it, but that was nowadays I feel like it's like, oh yeah, not a big deal. But the context in which that was announced, that was huge. The PHP and those frameworks, again, they've evolved a lot and they've improved. And I think Ruby on Rails has a lot of thanks should be to what Ruby on Rails brought to kind of this field of software, because ASP.NET, I don't remember, like what was the Java one? Anyway, it was building web apps was verbose and boilerplate heavy and painful. And what Ruby on Rails brought really was like a game changer. And I think that kind of focus on ergonomics and ease of use, at least from my experience back then, it was a while ago, I don't think anyone is even talking about that. And that, like, anyway, so that kind of pivotal moment, I really care a lot about trying to recapture that like initial magic that I remember. I do think things have gotten more complicated. Like there's a lot to be said about how simple things were in those days. Obviously, I can't come back and copy Ruby on Rails now, but I'm hoping that there'll be a path to bring back some of that opinionated, kind of streamlined, building things quickly, like everything kind of working together, following like best practices to get things done quickly. And part of the trade-off that you make with that is like it's not going to work for like if you need maximum flexibility, you're probably going to have to go off and do things custom. But again, is it possible to design a framework or a set of libraries that have that like can capture like the 90% case really effectively, plus have a ramped off-road, like a ramped escape hatch path where like you don't have to dump everything. So that's a big thing with Toasty is one thing I hear about ORM users is, well, like once I'm not in the happy path of my ORM, I have to get rid of it completely. And I understand that. And I'm trying to avoid that with Toasty. Turns out it's hard. And the reason why it's hard is if you look at Toasty, it's not even, I'm calling it an ORM because that's what people, like, I think that's the term people know, but mentally I'm thinking of it as a application level query engine. And I really am like, let's build a query engine. And that's a big project because as I think one of my, like the way I approach things, I drastically underestimate. I'm like, how hard can this be? But then I stick with it. So I started Toasty a while ago. It's definitely been a long road and a lot of figuring it out. It's really just been a side project, but it's really getting to the point. I think it's close. I'm really pushing to get to the beta, like obviously cutting a bunch of features. But if you look at the internals, it's really structured like a query engine where you talk about your application data model, you build up an application level kind of query, and the engine transforms it to the database level. And the reason why this matters for the escape hatch is I do think I will be able to implement a system where you can mix and match SQL queries with Toasty kind of level application queries. So you will have that escape hatch. Anyway, that is, the short version is, yes, I want there to be a high level web framework level kind of application building thing in Rust. I'm working towards there. If y'all want to help, Toasty is the first place because at the end of the day, like a high level web framework is just like your data model, how little code you start with data model and that thing, how little code can you write to get that to the UI, right? So I'm starting with Toasty, the data model, and then from there, I think it will inform the rest. And the best way to help is to get involved with Toasty, try using it, provide feedback, and come to Tokyo Conf. We can talk about in person. And yeah, I'm pretty excited about it.
Yeah, good luck with that. That's ambitious but very useful project, I believe, for the whole Rust ecosystem. Yeah, it would be great to get something like that. So we already invited folks to Tokyo Conf, to Portland, Oregon, not the other one. Okay, great. Unfortunately, our time is over. I have like a million of other questions, even in the chat, well, it's impossible to cover all of them. I think we covered quite a lot of topics about Tokyo itself and the Async Rust. Well, I love Rust. I believe it's a great language, so I hope we will be able to deliver a lot of new code in Rust, and it will be performed. By the way, my direct manager just a couple of days ago shared the story with me how he rewrote his service from Spring Boot to Rust, and now it's like he saved like 40 seconds of startup time, something like that, because of moving to Rust. That's something we can rely on with Rust.
Yes,
it is performant, really. Yeah. All right, great. Thank you very much. Yep. Thank you for joining us. Awesome. Thank you, folks. And
I'll say, feel free to continue the discussion. The Tokyo Discord, I'm there. If you want to talk about Toasty more, there's a channel there. Love to talk more as well. And hopefully someone will share the Discord link, Tokyo Discord link. But it's also on the Tokyo website.
Yeah, cool. It's right there. Okay, in chat. Okay, thank you and bye. Maybe see you. See you later.
Will do. Thanks for having me. This is fun.